Evening to all, a very good evening. So yesterday we have seen some questions on the Bernoulli's equation. So at that time also I have told that they are very important question. So another important topic is the NPSH, that is net positive suction head. Again, it depends upon the Bernoulli's itself. Okay. So one question which is asked in the gate examination, we will see. Storage vessel. Another important topic is the NPSH, that is not exposed to atmosphere. Absolute pressure is 10.3 meter of water has diameter of 3 meter and is initially filled with water to a height of 2 meter. The pump draws water from the vessel is located at an elevation of 5 meter above the bottom of the vessel. The frictional head loss in the suction pipe is 2 meter of water. If the vapor pressure of liquid at the temperature of operation is 3 meter of water, calculate the available NPSH. Okay. So basically NPSH is net positive suction head. Okay. So here net positive suction head basically means how much is the suction pressure, that is mostly it is equivalent to the atmospheric pressure. So it is P by rho G minus the vapor pressure of the system, that is PV by rho G. Okay. Minus frictional losses and minus Z. Okay, this Z is minus. Why? Because most of the time pump is keep above the tank. Okay, most of the time the pump is kept above the pipe. So that is why minus. So if pump is keep here, suppose if the pump is kept here, then the Z is 0. And if the pump is kept below the tank, then the Z is positive. Okay. So from this part you have to solve. So here if you see from the data, it is 10.3 minus vapor pressure they have given. It is 3. Frictional head loss is 3. Okay. And this is 2. Okay. And this is 2 is given in the question. Okay, so here it will be 10.3 minus 3 minus 2 minus 3. So you might be thinking that how pressure is in meter. So see here. Here P is Newton per meter square upon rho is kg per meter cube into g is meter per second square. Okay, so if you solve this Newton is force, mass, kg into acceleration, meter by second square. So this will cancel. So kg will cancel with this. Okay, and this will go upward and only meter will be there. So the unit of P by rho g is meter. So what is the meaning? इसका मतलब ये है सपोज कि हम जब बोलते हैं कि इस सिस्टम या इस सिस्टम के पास कितना प्रेशर है. ओके, सपोज समवन से इट इज 20 किलो पास्कल. लेकिन जब हम पंप की बात करते हैं तो क्या आता है? जब हम पंप की बात करते हैं तो यहाँ पे जो सबसे इम्पोर्टेंट क्राइटेरिया जो आता है दैट इज कि उस पंप से हम पानी को कितना ऊपर तक लेके जा सकते हैं, है ना. दैट इज इम्पोर्टेंट कि 1 स्टोरी पानी ऊपर चढ़ेगा कि 2 स्टोरी पानी ऊपर चढ़ेगा कि 3 स्टोरी चढ़ेगा. दैट इज वेरी वेरी इंपॉर्टेंट, है ना. दैट इज वेरी वेरी इंपॉर्टेंट फॉर द सिस्टम. ओके, so that is why we try to keep the units here in meter, है ना. कि 1 स्टोरी चढ़ेगा तो कितना मीटर ऊपर जाएगा, 2 स्टोरी चढ़ेगा तो कितना मीटर ऊपर जाएगा. Like this, the system will behave. Got it? That is why we calculate all the things which related to pump in meter. आया समझ में? Only in Bernoulli's equation you will see that related to pump that the calculations, okay, that the calculations are done in meter. Got it? आ गया समझ में? Okay. There are so many questions from the Hagen-Poiseuille, है ना. So in Hagen-Poiseuille equation, through a cylindrical tube, the radial profile of shear stress is okay. So what will be the profile here? So in the radial profile, it will be like this: dp by dl plus 2 tau by r is equals to 0. So delta p by l is equals to 2 tau by r. Okay. So tau is directly proportional to delta P by 2L into R. So tau is directly proportional to R. Okay, like this. So what will be system? Profile will be linear. Profile will be linear. Okay, so this derivation is asked so many times in the gate examination. Okay, on the basis of this, there are so many questions. Okay. Next, there are so many questions from the fluidization part. Okay. So if dP is given 1 into 10 to the power minus 3 meter, phi s is given 0.8, density of fluid is 1000 kg per meter cube, mu f equals to 1 into 10 to the power minus 3 kg per meter second. Okay. Particle density is 2500 kg per meter cube. G is 9.8 meter per second square. Okay. V naught is equals to 0.005. E equals to 0.5. Okay. So you have to calculate ratio. A ratio of viscous loss. Ratio of viscous loss to kinetic energy loss. Okay, so delta P by L equals to 150 mu V 1 minus epsilon square phi square dP square epsilon cube plus 1.75 rho V square 1 minus epsilon upon phi s dP epsilon cube. This is the most important equation, that is Argon equation. Okay, Argon equation. So this Argon equation, okay, this Argon equation is used basically to calculate the pressure drop in the pack bed and the fluidized bed. Okay. So here the first part, if you see, there is a viscosity term. So these are the viscous losses in this equation. So due to viscous losses, there will be pressure drop. And here there will be V square, velocity square. So there is a kinetic losses, kinetic energy losses. Okay. And in the question, they are asking the ratio of viscous losses to the kinetic energy losses. Means here this viscous losses is known as Cauchy-Kármán equation. And this is Bucher-Plummer equation. Bucher-Plummer equation. Okay. So just calculate this. It means in the question what you have to calculate the ratio of this. It will be 150 mu V1 minus epsilon upon phi s d phi square dp square epsilon cube upon 1.75 rho v square 1 minus epsilon s square upon phi s b epsilon cube. You have to just calculate the ratio of this. So calculate this. Okay, so if you calculate this ratio, it will be coming 10.71. What is most important thing is that you sometimes the gate may give you this equation and sometimes they may not give you. So have to remember this equation. Okay, you have to remember this equation. Okay, got it? Another question. Two different liquid are flowing through different pipes of the same diameter. In the first pipe, the flow is laminar with center line velocity V max 1. Whereas in the second pipe, the flow is turbulent. For the turbulent flow, the average velocity is 0.82 times the center line velocity V max 2 for equal volumetric flow rate in both the pipes. The ratio V max 1 divided by V max 2 is okay. So they are asking for the ratio directly V max 1 by V max 2. So for laminar flow, V average is 0.5 times of V max 1. Okay. This is for laminar. This you have to remember. And for turbulent, V average is equals to, which is given in the question, it is 0.82 times of V max 2. Like this. So here they are saying that volumetric flow rate is same. So Q laminar is equals to Q turbulent. So it is 0.5 V max 1 is equals to 0.82 V max 2. So as diameters are same, so area will cancel. Now V max 1 upon V max 2 is equals to 0.82 divided by 0.5. So like this you will calculate the answer. Okay. Next, on the incipient fluidization, the gate has asked so many questions. Okay. The question is a cylindrical packed bed of height 1 meter is filled with equal sized spherical particle. The particles are non-porous and have a density of 1500 kg per meter cube. The void fraction of the bed is 0.45. The bed is fluidized using air density equals to 1 kg per meter cube. If the acceleration due to gravity is 9.8 meter per second square, the pressure drop across the bed, incipient fluidization. So what is incipient fluidization? Incipient fluidization basically mean minimum pressure. Okay, minimum pressure required to keep the particles in the suspended form. Okay, minimum pressure required to keep the particles in the suspended form. That is the incipient pressure. Okay, so the formula is delta P by L equals to rho P minus rho 1 minus epsilon into G. So solve this. Okay, so here it is rho P, that is the density of particle is given. It is 1500 minus air 1 minus epsilon. Epsilon is nothing but a void fraction, that is 0.45 into 9.81. That's it. So what is the answer? You solve this directly, you will get answer. The important thing is that you have to remember that this is the formula for the incipient fluidization. That is the minimum pressure required to keep the particles in the suspended form. Okay, that is important. Sorry. Done. There's a one very good question on the basis of friction and the drag. It will clear most of your doubts. For fanning friction factor, F for flow in pipes and drag coefficient CD for flow over immersed bodies, which of the following statements are true? Okay, so statements are given. P F accounts for only for the skin friction. Q CD accounts only for the form friction. R CD accounts for both the skin friction and form friction. Both F and CD depend on the Reynolds number. T for laminar flow through a pipe, F doubles on doubling the volumetric flow rate. Okay, so this is the question. So just take a minute and think that what is important from and what is the difference between the F and CD. That will also I will tell you. Okay. Okay. So see, what is the difference between F and CD? F is friction factor, CD is drag coefficient. Okay, F is friction factor and CD is drag coefficient. So while talking friction factor, okay, here F is always a function of Reynolds number, whether it is a laminar flow or turbulent flow. Similarly, drag is also a function of Reynolds number. Okay, so S is correct. Both F and CD depends on Reynolds number. So F accounts for the skin friction, CD accounts for the form friction. It is not like that. Okay, skin friction is that which is acting on the upper surface. Okay, and form friction is that which is acting on this surface perpendicular. Okay, normal surface. Okay, so here we can see that accounts only for the skin friction and CD accounts only for the thing like this. So now you tell me which one is correct. So F accounts for the skin friction. Yes, this is correct. Okay. And CD for the skin and the form friction. Okay. And both F and CD depends upon the Reynolds number. So correct option is PRS. Okay. Next question. For a flow through a smooth pipe, the fanning friction factor F is given by F equals to M R the where RE is the Reynolds number and M is a constant. Water flowing through a section of this pipe with the velocity 1 meter per second. Result is a frictional pressure drop of 10 kilopascal. So what will be pressure drop across this section in kilopascal when the velocity of the water is 2 meter per second. Solve this. So if you see here, delta P is directly proportional to MRE. So it is 4 FL rho V square by 2D. And here F is MRE to the minus 0.2 into V square. So it will be V is 1.8. So here we can say that delta P is directly proportional to V to the power 1.8. So delta P1 V1 upon delta P2 upon V2 to the power 1.8. Okay. Now, can easily calculate delta P2 is equals to 34.8 kilopascal. Okay. One very good question on the friction. It will clear all your doubts regarding the friction, depending upon table given below. RE 10 to the power 2, 10 to the power 3, 10 to the power 5, 10 to the power 5. K by D 0, 0.001, 0, 0.001. Set 1, set 2, set 3, set 4. F, 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 F. 0.16, 0.016, 0.16, 0.0045, 0.016, 0.16, 0.016, 0.0055. Okay. It is 16 into 10 to the power minus 5, 0.0055, 0.0045, 16 into 10, 0.0045, 0.0055, 0.16. So solve this. So here if you see it is Reynolds number is low. So these two are laminar flow. And here you see it is turbulent flow. Okay. So for laminar flow, F is directly written as 16 by RE. So if you see it is RE, then this is correct. Okay, this is correct. In set 1 or set 3. Now this is same as this is also correct. Okay. Now the interesting point is K by D is roughness factor. So when the surface is rough, actually what will happen? There will be more friction. There will be more friction. So if you see here, the values are not changing. In fact, the roughness is changing. And here you can see the roughness friction is changing. So that is why set 3 is correct. So very interesting question. Okay. Okay. Any doubt? Know something about kinematic fluids? The stream function xy plane is given below. Psi equals to 1 by 2 x square y cube. Okay. The velocity vector for this stream function is okay. So you have to calculate the velocity vector of this stream function. So we know that u equals to del psi by del y and v equals to minus del psi by del x. So v equals to u I cap plus v j cap. So v equals to del psi by del y I cap minus del psi by del x j cap. So psi is given, that is 1 by 2 x square y cube. So del psi by del x is equals to xy cube. Del psi by del y equals to 3 by 2 x square y square. Hello? X square y square I cap minus x y cube j cap. This is the solution. Next question. As incompressible fluid is flowing through a contraction section of length L and has a 1D x direction, steady state velocity distribution u equals to u naught 1 plus 2x by L. If u naught is equals to 2 meter per second and length is equals to 3 meter, the convective acceleration is okay. So convective acceleration basically when something is divided by space, so it is convective, and something is divided by time, then it is known as local acceleration. Okay, so this point you have to remember. When something is divided by space, then it is a convective acceleration. And when divided by time, then it is a okay. So try to solve this. So convective acceleration will be ax equals to u del u by del x plus v del u by del y plus w del u by del z. Ax equals to u del u by del x. Del u by del x equals to 2 u naught by L after differentiation. So we will put the value plus 2x by L into 2 u naught by L. So ax equals to 2 u naught square by L 1 plus 2x by L. So ax at x equals to L, it is 2 u naught square upon L 1 plus 2L by L. Okay, so if you solve 2 u naught square by L square upon 3 into 3, that is 8 meter per second square. Okay, good evening. So in this way, the important thing, whenever it is asked with respect to space, x, y, z direction, then it is a convective. Okay, you have to apply convective. And if it is a local, then it is with respect to time. Then it is a local acceleration. In a steady, incompressible flow, the velocity distribution is given by velocity vector equals to 3xi cap minus pyj cap plus 5zk cap, where v is in meter per second. Okay, so in order to satisfy the mass conservation, the value of the constant p. So mass conservation is basically, what is mass conservation? Mass conservation is basically continuity equation. So it is del u by del x plus del v by del y plus del w by del z is equals to 0. Okay. So here if you see, it is 3 minus p plus 5 is equals to 0. So should be equal. Anna? Like this. Next, the local velocity of a fluid along a streamline can be measured by A is pitot tube, B is venturimeter, C is rotameter, D is orifice meter. Okay. So here if you see, pitot tube will always give you a local velocity. Okay, means the point where it is kept, it will give you velocity at that point. Okay. Venturimeter, rotameter, orifice meter. Rotameter is variable area flow meter. Okay, and venturimeter and orifice meter, constant area. Like this. So some questions are asked from this point also in the examination. Okay. Okay. So these are the most frequent areas from where the gate will definitely ask the question. So you have to do more practice on the Bernoullis and the fluidization. Okay. From this point, the gate normally asked every time one or two questions from this part. Okay. So that is why make sure whatever the question I have taken from that area, you practice more questions. And definitely these are the repetitive questions from this section. Okay.